look at a book which is written way before any of these softwares came. The book Molecular Thermodynamics of Fluid Phase Equilibria. In that book, there is a chapter, I think 4 or 5, which talks about the molecular basis of why which equation behaves better in a particular situation. And that gives a lot of guideline about which equation to choose. But this is mainly talking about mixtures and liquid phase non-ideality. When you talk about single phase, pure component, single component phase equilibria, then it is mostly about RT upon P and the molar volume. It is liquid phase non-ideality that you have to select the model and based on guidelines which you can pick from that book. Next question is about conditions of entropy for endergonic reaction pathway. I must admit I have no clue what is an endergonic reaction pathway. Abhijit sir, can you elaborate a little bit?
Yeah, endergonic reaction pathways are that which requires large amount of energy to initiate the reaction, that we call as the endergonic reaction pathway.
So the energy of activation is very high.
Yeah, right, exactly.
Okay. So the equilibrium and thermodynamics is not going to talk about the rate of reactions. So even if there is a large energy difference or a small energy difference, the rate of reactions are not proportional to that energy difference. And there is an intermediate state which we define as the transition state. And from the starting point to transition state, that energy difference is related to the kinetics. The starting, the intermediate, and the ending. The ending may be below, ending may be above. Thermodynamics is only about the starting and ending, and not about that intermediate state. So the kinetic answers are never given by thermodynamics.
Okay. Yeah, exactly.
Okay. So Eyring-Polanyi expression. Now, once again, what is that?
See, Eyring-Polanyi expression is the expression which is plotted. Actually, that equation particularly it is in the form that is mentioned. Actually, let me read that particular expression, which is in the form of y equal to mx plus c, and it is nothing but a plot of ln of k by t plus delta s that is equal to delta h upon rt plus ln of kb upon h plus delta s upon r. So this is upon polynomial equation given by Eyrings, and it is nothing but it is in the form of y equal to mx plus c. So here
mx plus c will become a linear equation.
Yeah, right, exactly, linear,
not polynomial.
Yeah. Okay, and this particular equation, from this equation I have read in many research papers, they are estimating particularly delta S and delta H, particularly for the reactions. So where ln of k by t, k is nothing but particularly your absolute rate constant, which is calculated at particular temperature related from this delta H and RT, and delta S we are estimating particularly as entropy change, particularly from this expression. So just I put forward this equation.
Let me tell you one thing, although this specific one I'm not really aware of, but okay, let me tell you one thing, that many of these equations which are written and can be written and they are fundamentally sound as well. Okay. However, to get a reasonable number value from them, the kind of accuracy that you require in the experimental measurements is very high.
Okay.
Usually experimental measurements have so much error in it that if you try to conclude such numbers of delta H or delta S from that, there will be a lot of plus minus in it.
Okay.
So that is the only precaution. Otherwise, these kind of equations are there and you can, they are fundamentally correct, nothing wrong with that. Okay. But when you actually calculate it with plus minus, let's say small error in analysis of 5%, how much difference it will make? Then you realize that there is a huge difference possible to the values we are concluding on the basis of that. So
yeah,
that is word of caution.
Yeah, I'm facing the same problem in the calculation. That's why I asked the question.
So these equations by themselves are correct, but many times not really practically usable based on
Okay.
experimental data.
Okay. Thank you, sir. Okay. Okay.
Right? So the next part I have in mind will be about mixtures, but let us see if I have something remaining even with pure components. So this I have shown the Maxwell equation and its use. This equation, say for example, I am calculating entropy residual. I am going to need an integration of del S by del P dP. And Maxwell equations is what help us tell about changes in conceptual properties being linked to changes in measurable property. So del S by del P at T is equal to negative del V by del T at P comes from Maxwell. And if you can see the right hand side, V, T, P, they are all measurable properties. And on the left hand side, we have change in entropy with pressure at constant temperature. This answer is given by something which is measurable. So I can substitute this value in this integration here and indeed obtain the S residual. So we will, if time permits, solve a problem of turbine tomorrow where we will be using this. So del V by del T will be introduced instead of the del S by del P to get the answer. Even for pressure explicit equation of state, where I cannot get the del V by del T, I can write it in terms of del P by del T and obtain the S residual. So obtaining these residual properties is a requirement for calculating the property changes, and that is where we use those equations of state which represent the PVT behavior. And the need for PVT behavior is to obtain the real fluid properties. Had materials been all ideal gases, there would never have been any liquid. Had materials been ideal gases, enthalpy would never change with pressure, and therefore the Joule-Thomson expansion would never be giving any cooling. So real fluid properties are important. Ideal gas or the simplified gas equation is only a starting point for us to understand that. So I am going to leave this presentation with Dr. Patil. So you can maybe get it from him or you have it in standard books. But when we solve the problems tomorrow, we will be looking at these equations once again. So this is about enthalpy transformation. You will require enthalpy residual. So enthalpy residual in terms of pressure explicit equation of state you derive, put the equation of state here and then solve the infinity to V integration either numerically or analytically and then obtain the enthalpy residual. Specific heat changes is the next thing that we have to tell them, that what is listed in handbooks is not CP. What is listed in handbook is CP star or CP0. That means CP of that gas if the pressure was reduced to 0. The ideal gas state specific heat is listed in handbook. And at every different pressure, the CP will change. So variation of CV with volume or variation of CP with pressure is again linked to F of PVT, the volumetric equations of state, and we can obtain that expression as well. Having completed the real fluid property calculation, the next thing we will be looking at is this mixtures. Now mixtures, there are some concepts which we have to explain before we start solving problems. One of them is of partial molar property. An extensive property differentiated with respect to moles of only one component, pressure and temperature fixed, other moles not changed, gives us the partial molar differential. And in the equations of dg, du, dh, you will have the partial molar Gibbs free energy which appears for open systems. And the partial molar Gibbs free energy is also called chemical potential. And just like G molar was equal to G molar in vapor and liquid, we will have Gi partial molar equal in both the phases for phase equilibrium. So multi-component phase equilibrium, then we'll have equality of mu I or the Gi partial, which are linked with Fi bar, the fugacity of a component in mixture. So partial molar is written with a tilde sign, the curvy sign, which probably will be there on the next slide. But Fi bar is not the same and it is written as bar. Every symbol that we use, if we keep that practice, that every symbol that we use, we list it separately. In fact, what I do is keep a left part of the board always for new symbols introduced in the last few weeks. So those are first written by the student themselves, and some of the equations that we have derived in the last few weeks will be always there on the left side of the board before I go to the classroom. And that always helps in doing the next steps as a dependent on previous steps. And once you have done equations in that fashion, for any question, start always with the fundamentals and get the answer. Do not start with some equation as a God-given equation, because no equation is God-given. You have derived them. So derive them from first principles, from various basics, and just 3 or 4 steps max, and you will get the required equation. But you should always remember the chain from the first equation that you wrote from first law of thermodynamics, that du is equal to TdS minus PdV, and from that you should arrive at the equations you need. So if you do that partitioning of the board, one part of the board, not even one half, you require barely 1/4 or 1/5 of the board just for new terms and the latest equations that you have derived, and then do the class with the rest of the board. So that helps a lot in students connecting things with each other. Then you talk about property changes of an ideal gas. Property changes of an ideal gas and ideal mixture are same. So therefore the concept of ideal mixtures of real components, and then the excess properties. But the most important of those entire properties would be the Gibbs energy. So for an ideal mixture, Gibbs energy can be calculated as mole fraction times pure component energies plus the delta G of ideal mixing. And for an ideal mixture, the partial molar Gibbs free energy or the chemical potential of that component is simply Gi plus RTL and Xi. And for an ideal solution, Fi bar is equal to Xi into pure component Fi. So this is the Lewis and Randall rule of ideality, which is basically ideal mixture with respect to delta G. So ideal with respect to delta H, delta S can be different, but ideal with respect to delta G gives me this, which is the Lewis and Randall rule for ideality, which is what we use for mixtures in non-ideal conditions. So for vapor phase, liquid phase equilibrium, mu I vapor equal to mu I liquid. And when you expand the Gi partial and you get to Fi bar, you have to write that Fi bar of the vapor phase and Fi bar of the liquid phase. Fi bar of the vapor phase can be written using equations of state. So you can write it as Pyi into Phi I bar. And for ideal mixtures, Phi I bar gets converted to Phi I. Never give it just that it gets converted. Show and derive so that they feel convinced. Because the biggest problem in thermodynamics equations is students are never sure which equation to use where. And that happens because they have not derived it, but from the book they have directly taken it. So keep a practice that any equation you will derive on the board in front of them, so that they get the confidence that they can also derive it, and only then use that equation. So Pyi Phi I bar becomes Pyi Phi I, and if the gas is at ideal gas conditions, pressures are low, only then the gas phase Fi bar becomes P into Yi. Fi bar on the liquid phase side, on the other hand, is expressed as activity times Fi of the pure liquid. Activity is written as a product of activity coefficient and mole fraction. If the solution is non-ideal, activity coefficient will be non-unity. If it is ideal mixture, activity coefficient will be 1. But Fi of the pure liquid cannot be obtained from equation of state, because liquids are not adequately described by equations of state. And therefore, that FIL is linked to vapor pressure of the pure component. Vapor pressure of the pure component can be converted to fugacity of the vapor at the condition of vapor liquid equilibrium of pure component with phi is. So PIS into phi is gives me FIV, but at pressure PIS. From pressure PIS to pressure P, if I have to convert that Fi liquid, I require the Poynting correction, which is about variation of fugacity of a liquid with pressure. which we obtained by looking at variation of Gibbs free energy with pressure at constant temperature. So dg is equal to vdp we use, and we get the Poynting correction. So the full equilibrium equation is actually P yi phi I bar equals gamma I xi into PIS into Poynting correction into phi I at saturated conditions. And it is only when gases behave ideally that the phi and Poynting corrections become one, and only when liquid phase mixture behaves ideally that gamma I is one, and only under these 5 assumptions that you get the Raoult's law that Pyi is equal to xi psi. And most commonly, if the pressures are low, all other coefficients would be 1 except the gamma I. The gamma I is not dependent on pressure. Gamma I is about liquid phase non-ideality, which is not at all connected with pressure in any way. And for most binary mixtures or multi-component mixtures, the gamma I would not be 1. So Raoult's law is actually not applicable in most conditions unless the two molecules are not even neighbors or friends, but brothers. So that means the members of same homologous series, ethane, propane, pentane kind of a series, and they should be of similar size. So if you are mixing ethane with decane, there would still be an activity coefficient. But if you are talking about propane and butane, adjacent members in the homologous series, it is only then that activity coefficient can be taken as 1. And with this, in fact, you should take one problem at least with LPG, because LPG is a mixture which they are familiar with. It is propane and butane, and you should do a calculation of vapor liquid equilibrium where gamma I is equal to 1, but the phi I bar, Poynting correction are all required for this equilibrium. And LPG cylinder, when it is full, it has more propane in it. When it is nearly empty, it has more butane in it. It can be easily shown that at atmospheric temperature, the vapor pressure of that LPG becomes less and less as the cylinder becomes empty. And the reason is, instead of more propane, now it becomes more butane. While the pressure is becoming less, the gas that comes out will be richer in butane, and therefore its calorific value will be higher. And that is why you don't notice it in the usage so much. Propane butane mixture is typically the LPG. So therefore, please do solve one problem at least for them, where Pyi phi I is equal to xi into pi sat into phi I sat into Poynting correction. That means all other terms there except the activity coefficient is what you need for that. Then you talk about Raoult's law, and where yi upon xi is used as ki in distillation calculations, and Raoult's law is obeyed under very, very few mixture conditions. But modified Raoult's law, which is Pyi is equal to xi gamma I pi sat, is used at lower pressure. This is the full equilibrium equation. This is the Poynting correction term. And this modified Raoult's law is applicable at low pressures, not Raoult's law, because gamma I would rarely be equal to 1. So then I normally take one problem where the phi's can be taken as 1, unlike the LPG problem, but gamma I is not 1. So here I am going to take one problem like that with you, where I'll be having a mixture of two hydrocarbons where there is non-ideality in the liquid phase. So how do you connect and how do you correlate those experimentally measured values? You can calculate the experimentally measured activity coefficient through this equation. Pyi measured divided by xi known and pi sat known, I can get the gamma I experimental, and from that gamma I experimental, I should be able to obtain the excess Gibbs free energy, for which I need to derive the relation that Gi partial molar excess is RTL in gamma I. So once I have measured the experimental gamma I get experimental Gi partial molar excess, and summation of xi Gi partial molar excess will be Ge. This Euler theorem itself we should derive when we are deriving the Gibbs-Duhem equation. And the Gibbs-Duhem equation forms the basis of entire mixture equilibria and the thermodynamic consistency of vapor-liquid equilibrium data. That also we should be discussing, and then deriving this equation and calculate the experimental GE from experimental gamma I, which is obtained from experimental PTXY. And once we have obtained the GE experimental, then we have to think about correlating that. And for correlation, we must use equations which are valid as per Gibbs-Duhem equation. And once we have the correlations which are valid as per Gibbs-Duhem equation, then we can do this partial molar differentiation as in GI partial molar, and divided by RT will give me ln gamma I. So I can calculate from that correlated value of GE required activity coefficient, and from the activity coefficient then I can calculate the vapor liquid equilibrium. That is what the numerical problem we are going to do tomorrow. So that a distillation column can then be described as something where alpha as a model can give you Yx but cannot give you temperatures and pressures as required, whereas a thermodynamic model can, and alpha is a single parameter. Similarly, you have thermodynamic models which can be single parameter also, but they will have more consistency with that thermodynamics in terms of correctness of those equations. That thermodynamic consistency can be checked in multiple ways. One of them is this integral method. Ln gamma 1 by gamma 2 integral is equal to 0. Then we have to look at the dln gamma by dx slope. We have to look at the ln gamma versus x2 slopes being related. x1 dln gamma 1 by dx1 plus x2 dln gamma 2 by dx1 is equal to 0. Those kind of consistency checks. And then fitting the GE models. You take an experimental set like this. This is for benzene and trimethyl pentane. I have the pure component vapor pressures and I have the experimental XY. I could have predicted using Raoult's law, and then I would see that these values are indeed different from what Raoult's law gives. So which means this is a deviant system from Raoult's law. Pressures are low, so all the 5 values are 1, and still there is a deviation, which means activity coefficient is not 1. So calculate the experimental activity coefficients, and then you can see as x1 tends to 1, activity coefficient of 1 tends to 1. And as x2 tends to 0, that means x2 tends to 1, that means x1 tends to 0, gamma 2 tends to 1. And ln gamma 2 will also, of course, tend to 0 when gamma 2 tends to 1. But besides, in addition to that, even the slope of ln gamma 1 with x will tend towards 0. That also you will see graphically. We will be looking at that tomorrow's session, which I will be doing from Mumbai. So that time we will be doing these calculations numerically on the calculator, except the graphing part, which I will do using another software. I will be doing it on the screen. But the calculations part, I would want you to do with your calculators tomorrow. So predictions can be done using Raoult's law, but fitting and correlation is possible with Margulies model, Redlich-Kister model, Van Laar model. Then you have there are 3 or 4 other models as well, which you will be using. Some of them Wilson's equation, or you will have the truncated form of the Voel's expansion. And then we will talk about predictions using those group contribution methods. Then one of the prediction method, which is not really prediction method, it is part prediction, part experimental correlation, namely the UNIQUAC, and then the full predictive method, which is UNIFAC. And why UNIFAC predictions are to be used only when experimental data is not available, because it cannot be as accurate as correlating with any of these equations, and correlations cannot be done unless you have experimental data. So therefore, if you have experimental data, use any of these correlations. And once again, the question comes, which of these models, whether you use Wilson's, whether you use Renan and Proudnitz, NRTL, or UNIQUAC for correlation, those decisions you have to take on the basis of experience or on the basis of the molecular thermodynamics, as I had explained just a little while back. So choosing those equations, you can explain a little bit, but our job at undergraduate stage is explaining them how those equations work. A little later, you can then, if time permits, tell them which equation to use at what kind of conditions. That amines are better handled using NRTL. That's a matter of experience. There is no derivation involved in it, no theory involved in it. The only theory which explains why it is that way is that maybe carboxylic acids dimerize, amines have these properties. So these are more empirical things. So that you can use the molecular thermodynamics books for that. But the fun of thermodynamics is more in fundamental based derivations and use of them for practical applications. So for binary molecules model is Ge is equal to Ax1, X2, and then you can show the fitting. We'll be doing that calculation. This is the Wolf's expansion with multiple terms. Wolf expansion, if you truncate it to first term, it becomes equivalent to Van Laar equation. And Van Laar is a two constant one. Redlich-Kister can be expanded to multiple terms. Wilson's is a two parameter equation, but this can be used for multiple components, unlike the other equations that Margules and those equations, Redlich-Kister, they are meant only for two components, but Wilson's can be multi-component. Similarly, NRTL can be extended to multi-component. This looks like a 5 parameter equation, but it is actually 3 parameters. You require the alpha and then the tau12 and tau21. And most mixtures, alpha value of some 0.2 or 0.3 is used. So it becomes effectively a 2 parameter. And for every binary pair inside a multi-component mixture, you will require 2 constants, even for Wilson. So if you have 3 component mixture, there are 3 possible binary pairs. So for each binary, you require 2 constants. So you will require 6 constants when it is a ternary mixture. So you never actually model ternary using ternary data. So you take different binary mixtures, obtain the binary parameters, and then make a prediction. Not really a prediction. You use correlation of binary to make a prediction for ternary and then compare the experimental data of ternary with it. Or the Redlich-Kister expansion, which has indefinite terms in it, and each term has a particular role. The first term makes it Margules equation, the parabolic behavior of excess gives free energy. The second term makes it the skewed parabola on either side of x equal to 0.5 with this b into x1 minus x2. This third term will make that parabola either flat or sharp, and that kind of explanation you can only give graphically or by numerical problem solving. So we will see how to solve those problems. And then we come to predictive models, the simplest one being regular solution theory. Regular solution theory requires delta U vaporization, and that is obtained by delta H vaporization minus RT. And the fact that it says that phi1 delta 1 plus phi2 delta 2 gives me delta mix, and that is the basis of obtaining the delta U vaporization of the mixture, and therefore we get finally the RTL and gamma 1 predicted like this. However, the original development of this equation was not through the experimentally measured delta H vaporization. The origin of this method is in Van Laar's work, which was based on van der Waals equation of state, and therefore he had said that van der Waals equation can be used for liquid phase and entirely predictive, not even delta H experimental required, was the original regular solutions. Then the Hildebrand and Scatchard's regular solution theory, which incorporated the experimental delta H vaporization to obtain the small delta, the solubility parameter, and also the fact how it is related to polymer solubility in solvents. So if a polymer is soluble in one solvent, finding a second solvent of it for it can be done using the delta H vaporization and the calculated small delta value, which is used as the solubility parameter. And this is the first predictive method, which is the simpler one. Then there is a predictive method of Unifact, which expresses the excess gives free energy as 2 parts, combinatorial and residual. Combinatorial is about the size and shape of the molecule. Residual is more about the chemical nature of the molecule, which is typically said as energy of the molecule. Between these two, we have a predictive method. Correlative methods are useful when you have experimental data available. Predictive method is to be used only when there is absence of data. And this is the list of models. And I think your question about which models to use was more about this. You have various liquid phase non-ideality models. Margulis 2 suffix, 3 suffix. 3 suffix will be equivalent to Redlich-Kister expansion, 2 terms. Then the Bowles expansion, Wilson's equation, Renan's, Uniquac. These are all correlative models. Uniquac has part predictive, part correlative. So it is actually a correlative model. And regular solution, which predicts only positive deviations from Raoult's law, and Unifac, which can of course predict both ways. And Unifac is very useful for petroleum fractions, a little bit for petrochemicals, but functional groups, when they become more complex with fine chemicals, Unifac model is not a satisfactory model at all, and you have to use experimental data and correlations for such models. Phase equilibrium, once you have learned with VLE, then we have to talk about liquid miscibility, how oil and water do not mix, phases split, and you get two different liquid phases in equilibrium, and how the partition coefficient of a solute in the two liquids can also be calculated using the activity coefficient models of thermodynamics, which you have learned through vapor liquid equilibrium. That has to be connected here. And then the gas liquid equilibrium. Why is it different from vapor liquid equilibrium? Why gases are different from vapor related to their critical temperature? And then the Shire-Proudnitz correlation, as well as the second method, which is based on mixture fugacity coefficients for gas liquid solubility. Its connectivity with Henry's law and the experimental Henry coefficient, which can be calculated using thermodynamics for the gas liquid, and then the solid liquid equilibrium, leading to dissolution of solids into a liquid phase, and its relevance for fractional crystallization as a purification technique. So vapor liquid equilibrium as the basis for phase equilibria has to be then extended to liquid, gas liquid, and solid liquid equilibrium before we look at reaction equilibria. So next step is about reactive separations and some of the success stories about how even Fritz Haber's work about making ammonia, Bosch as a chemical engineer joining hands with him to make it as a Haber and Bosch process to make ammonia for the Germans for the World War, which later on became the fertilizer prime, and how the same amount of land could now produce 4 to 5 times more food, without which the world's population at the beginning of 20th century would not have been fed at all by this time. And what is the contribution of that single development of making of ammonia for food being available to people? And that reaction is limited by equilibrium. And what we learn as the principle about pressure, the Le Chatelier principle, is actually used in designing that ammonia plant. At higher pressure, you can push the equilibrium towards right. So once you link it to practical importance, then they learn about those equations more readily. And then you derive this equation that mu I is equal to 0, and that therefore it is linked to delta G of the 0 of the reactions. And then the definition of K, the equilibrium constant, as a ratio of component moles raised to nu I, the coefficient in the balanced reaction equation. This is for the ideal gas. Then for the real gases, you will have slightly different terms. So you take the equation, some simple reaction like CO plus steam reforming, giving you CO2 and hydrogen with various mole ratios. First as an ideal gas reaction only. Then you talk about how does the K get calculated at different temperature. Delta G, which is calculated at T naught, I can get the K at another T once I know the delta H, or with the full equation once I know the delta H and delta S, which is related to the CP changes, and I get the KT at any temperature. And couple more problems at another temperature, one very important one being sulfuric acid, SO2 going to SO3 is an equilibrium limited reaction at atmospheric pressure. So we still don't have to talk about non-ideal gases, an ideal gas reaction. And this is where I normally introduce the entire flow sheet of sulfuric acid before even I talk about ammonia process, the sulfuric acid process, and how those DCDA process becomes important. And what does it mean by multiple converters? Why is there is a temperature change between converters? And how is it that the fourth converter actually is a finishing one, which gives very little sulfuric acid produced extra, but it takes care of the pollution issue, and how that becomes the main part of the sulfuric acid plant. And then talk about calculating those reaction equilibria of SO2 plus oxygen giving you SO3. Then comes the ammonia reaction, which is at higher pressure, 1:3 hydrogen mixture at 101 or 200 atmosphere pressure, but at higher temperature to have a faster kinetics. And then finding equilibrium composition will require the use of non-ideal gases as well. So instead of having ideal gas equation, then you will require 5 values calculated using this for the reaction equilibria of ammonia reaction formation. So this is an example of CO multiple reactions, because it is not only one reaction at a time. Steam carbon mixture typically used to make the producer gas. You will give all the data which is not required as well, but they have to pick the required data. This is for synthesis gas to give you methanol or steam. This is the steam methane system. You may have steam carbon system. Many cases of multiple reactions happening simultaneously. And how do you solve for simultaneous reaction equilibria? That comes towards the end. And once you do simultaneous reaction equilibria as well as non-ideal gas reaction equilibria, your student at the end of 2 thermodynamics courses will feel very confident to handle thermodynamics and would realize that thermodynamics is a subject of practical applications, not just abstract equations. And we can achieve this with our thermodynamics student. Not only it will give you tremendous pleasure, but years together your alumni will be coming to meet you and saying how they find it very useful in the design industry if they are, or higher education if they are, that the thermodynamics course is no longer something to be scared of, no longer something which is an abstract one, no longer something where there are too many equations and too many symbols, but something which is their friend, something which is a practically useful subject. The subject forms the basis of many other chemical engineering subjects, but while teaching those subjects, nobody talks of thermodynamics. They will, let's say, even distillation will be started with alpha, or if you're talking about extraction, it will start with a distribution coefficient. But that the origin of those numbers is in thermodynamics is something we have to tell them while teaching thermodynamics. Once we do that, thermodynamics will no longer be a subject to be worried. Obviously, in a period of 2 hours, I cannot fully express my excitement of teaching thermodynamics over more than 20 years. But I have tried to give you a glimpse. And if some of you pick some of the ideas which I have presented here, and some of the ideas that I'll be talking tomorrow about with numerical solution of problems, it might help you in helping your students. So thank you for your attention, and any question, please pose your questions.
Any participants is having any question, please ask.
Answer either from chat or from oral questions. मला वाटतं लोक चहा प्यायला गेलेत. काय पाटील सर? Numericals we will be doing with equations of state solving, calculation of the fugacity coefficient G minus G star. Then we will be doing a numerical with vapor liquid equilibrium, taking a real data and calculating the excess guilt free energy and fitting a model. If time is left, then I'll be doing at least one numerical with reaction equilibrium. But the ones which require the use of those calculator features is the one which is for the single component, the equations of state and calculation of residual properties and so on. few experiments in UG curriculum. Indeed, it is possible, and it is important that you should have liquid-liquid equilibrium, some equation experiment on vapor-liquid equilibrium. You should have in undergraduate thermodynamics so that they can link what they learn in the class with that practicals. But somehow in our institute, we do not like the idea of one subject and its practicals. So we do not have practicals for thermodynamics, for mass transfer, for separations like that. We have a chemical engineering laboratory where all these experiments are there. Yes, we will be doing numericals on non-ideal systems. Oh, thank you, ma'am. My pleasure. And of course, I'll be with you tomorrow. I'll be back to Mumbai tonight, and tomorrow in the afternoon, our session will be there again, and there we'll be using calculators.
Thank you, sir. And now I request Professor P.B. Danke, sir, to deliver vote of thanks.
On the behalf of Organizing Committee and Chemical Engineering Department of PUPIT Sangli, I would like to express our sincere thanks to Dr. S.S. Bhagwat sir, Professor ICT Mumbai, for delivering elaborate presentation on chemical engineering thermodynamics. Sir has highlighted the topic like evaluation of concept of thermodynamics, laws of thermodynamics, relation of thermodynamics and chemical operations, types of thermodynamic operations, VLE and ideal and non-ideal systems, Gibbs-Duhem equations. I hope all the participants are happy with these sessions of Dr. Bhagwat sir. So, thank you Bhagwat sir for this presentation.
Thank you. It was a pleasure. So we'll meet tomorrow again.
Yeah, dear all participants, next session will start at 1. Okay, so please be there at 1 o'clock. It's on Sonikesh.